Hey guys, so last lecture we talked about the limit laws. In this video, what we're going to do is I'm going to go over the examples in my PowerPoint that I didn't do in the class last time. And those examples are going to illustrate two things. First of all, a lot of the examples we're going to do is just going to be more practice, similar to the stuff we've done in class. So if you understood the limit laws in class, then it's going to be just more practice, which can't hurt. But then there's going to be a few examples where there's little subtle things that we need to talk about. So I want to make sure I go through those examples too. So you will, if you completely understood what I went over last lecture, there's still going to be something to learn. So we're going to practice and we're going to learn some new stuff. And guys, please make sure you guys let other people in the class know that you need to watch these videos. I know I've mentioned it in class, but when you see this video posted online, if you know someone else in the class, just remind them to watch it, because on quizzes and exams and stuff, I won't just put things I go over in class. If I put anything on the video, it's fair game for the quiz. So I just want to make sure you guys spread the word so as many people as possible watch the video. All right, so let's get started. Okay, so let's see what this says. The graphs of the function f and the function g are given. So the graph on the left is the function f, the graph on the right is the function g. Use them to evaluate each limit if it exists. If the limits don't exist, explain why. Okay, so on the next slide, it's going to tell us what limits it wants us to find. Okay, so here are the different limits that we're going to find in this example. I'm going to go out of order because some of them are pretty easy and straightforward, and some of them are a lot more difficult. So I'm going to do the easy, straightforward ones first, and then we'll do the difficult ones last. So let's look at part A. Okay, so it wants us to find the limit as x goes to 2 of f of x plus g of x. And we're going to basically apply the limit law, which it tells you you're going to put the limit in front of each thing separately. But you can only do that if each limit exists. So I want to first figure out which limits exist. I want to know if the limit as x goes to 2 of f exists, and if the limit as x goes to 2 of g exists. So let's go back and look at the picture. All right, so I want to know limit as x goes to 2 of f. Limit as x goes to 2 of f of x. Well, if you look at the picture, the f is the one on the left. Here's 2 on the x-axis. And so if you start on the left side, find the left-hand limit, as x goes to 2, we're headed towards that open circle. So it looks like we're headed to the number 2. So the left-hand limit exists, and it's 2. If you're going to do the right-hand limit as x goes to 2, you would start on the right and move towards this open circle. And again, you're headed to 2. Oops. So this limit is 2. So the limit as x goes to 2 exists, and it's 2. The limit as x goes to 2 of the function f exists, and it's 2. We also need the limit as x goes to 2 of g to exist. Limit as x goes to 2 of g of x. All right, so on this picture, on the x-axis, here's the number 2. And let me just look at the left and right-hand limits real quick. So if I was doing the left-hand limit, I would start on the left, and I'd head towards 2. And so we're going to be heading to the right there, and it looks like we're headed to the number 0 on the y-axis. If you start on the right, so somewhere here, and you start heading towards 2, and again, we end up with 0. So it looks like the full limit is 0. So the limit of each one exists. The limit as x goes to 2 of f is 2, so it exists. And the limit as x goes to 2 of g is 0. That one exists as well. All right, so let's go to the problem now. So here's the way you're going to write it. Basically, you're going to write the following. First, we have to write down that the limit of f exists. So I'll call that number 1. The limit as x goes to 2 of f of x, we found in the previous slide that equals 2. So it exists. Okay. Then we have to write down which other limit? Just the limit of g by itself. So we'll call this the second thing. Limit as x goes to 2 of g of x, we found was 0. So it exists. Okay, so then we just apply the limit law. We just write so by 1 and 2. The limit that we want. So here's the limit that we want. So I'm writing the original question down. Now what I want you to do is I want you to show me the limit law. So don't just go straight to the answer. Apply the limit law. The limit law says when you're taking the limit of sum, you can put the limit in front of each function separately. So you can write limit as x goes to 2 of f of x plus limit as x goes to 2 of g of x. So we applied the limit law there. And again, this step here, going from here to here, can only be done if the limit of f and the limit of g exists, but we have the limit of f exists and the limit of g exists, so I'm able to do that. And then we can finish it off and say, well, limit of f is 2, so we have 2. Limit of g is 0, and so the answer is 2. Okay, so that's the answer to that one. It's pretty straightforward application of the limit laws. The next 3 will be the same. Let's go ahead and look at the next one. Okay, so we're jumping ahead to C, and this one's asking us to find the limit of f times g as x goes to 0. Once again, we need to look at the graph first. I need the limit of each one to exist. So let's go ahead and look at that now. All right, so we need the limit as x goes to 0 of f to exist, and we also need the limit as x goes to 0 of g to exist. Okay, so if we look at f, on the x-axis, x equals 0 is right here. So to see if that limit exists, I'm going to be thinking of left and right hand limits. So I'm going to first start on the left of 0, so somewhere here, let's say, we'll start here. And I'm going to be moving towards x equals 0, stay on the graph, so that means we're going to be moving that way. And as we head that way, where do the y coordinates look like they're going to? Looks like they're going to 0, because this y coordinate here is 0. All right, if you start on the right side to do the right hand limit, let's say we start here, and again, you head towards x equals 0. So you head this way. Again, looks like the y coordinates are headed to 0. So the left hand limit is 0, the right hand limit is 0, so the full limit is 0. So that limit exists, so that's good. Now for g of x, again, x equals 0 is right here. So if we're going to look at the left and right hand limit to try to figure out what the limit exists, what the limit is. So I'm going to start on the left of 0, and again, move until you get towards x equals 0. The y coordinates look like they're headed to this number here. I don't know what that number is, but it's headed to that number. Wherever this dot is, looks like we're headed there. The right hand limit, you would start on the right. Let's say we start here, and you'd move again towards that same spot, move to the left until you get towards x equals 0. Both ends look like they're headed to the same spot. Now I don't know what that number is. What does it look like? It's somewhere between 1 and 2. This is 0 here, this is 1 right here, this is 2 here. So it's somewhere between 1 and 2. It's going to turn out not to matter. But if you want to make a guess, you can say, oh, maybe like it's 1.4 or something. Again, it's not going to matter because this problem we're multiplying. It's going to end up being 0 times 1.4. So 0 times whatever it is would have been 0 anyway, so it doesn't matter. But let's go ahead and write 1.4. Okay, so the limit of f exists and the limit of g exists, so I'll be able to do this problem using the limit laws. Okay, so to do this limit, we're going to need the limit of each one of those functions to exist. In order to find the limit of f times g, we need the limit of f to exist, we need the limit of g to exist, and then we can apply the limit law. In the last slide, we saw that they do exist, so let's go ahead and just write that down. So first thing I'm going to write down is that the limit as x goes to 0 of f, well, it's 0, so it exists. So that's good. Then we need the limit as x goes to 0 of g of x to exist. And it did, as we saw on the picture, and it was something like 1.4, so it exists. Okay, so since each limit exists, we can find the limit that we're looking for using limit laws. So by 1 and 2, the limit we're looking for, so I'm just going to write down the question again. Limit as x goes to 0 of f of x times g of x. The limit law says you can put the limit in front of each one, so we're going to write the limit as x goes to 0 of f of x times limit x goes to 0 of g of x. Again, right there I applied the limit law. Make sure you show me that step where you apply the limit law. But again, you can only apply the limit law if each individual limit exists, and they do because the limit of f exists, the limit of g exists, so I'm allowed to make this step from here to here. Okay, and then now I can go ahead and just write down what these limits are. So the limit of f is 0. Let me put it in parentheses here. Then the limit of g is 1.4. They're getting multiplied together, and we get 0. So the answer is 0. And again, you see why the 1.4 didn't matter? If it would have been 1.7 or any number at all, the answer would have been 0. All right, so that's the limit of f times g. All right, let's try another one. Okay, so here, again, it's multiplication. This time the functions are, so x cubed is one function and f of x is the other function. They're being multiplied. I want to put the limit in front of each thing separately, but I can only do that if each individual limit exists. So we know that the limit as x goes to 2 of x cubed exists because that's a limit law. The limit as x goes to 2 of f, we need to make sure that exists. So let's go ahead and look at the picture first. So we're looking at x goes to 2 of f of x. So we're not going to be looking at the picture for g here, but we're just trying to see, does this limit exist? Limit as x goes to 2 of f of x. Does that exist? So 2 on the x-axis is right here. To figure out if this limit exists, we're going to think about left and right-hand limits. So left-hand limit, you want to start on the left of 2. So somewhere on the left of 2, but on the graph, let's say here, this is at the left of 2 on the graph. And you want to move to the right towards x equal 2, but stay on the graph the whole time. We're going to be moving this way. It looks like we're headed to where that open circle is right there. Okay, we're headed there. And that open circle looks like it's at 2. So the outputs look like they're headed to 2 if you just look on the left side of x equal 2. Right-hand limit, again, you would start on the right of x equal 2 on the graph, so somewhere here, let's say. And we're going to move towards 2, but stay on the graph, so we're going to be moving this way. And again, we're headed to that open circle, which has y coordinate 2. So it looks like this limit does exist, because the left and right-hand limits look like they're both 2. Okay, so this limit does exist, and it's 2. Okay, so that should be enough. We could be able to do this problem now. Okay, so in this example, the functions are being multiplied together. And so we want to use the limit law that applies to when two functions are being multiplied together, which means we want to write the limit of x cubed times the limit of f of x, which we will write, but we can only write that if each individual limit exists. So that's what we're going to write down first. Okay, so let's see. So we want to write down, first thing I want to write down is that the limit as x goes to 2 of just x cubed. I want that to exist. And it does. That was the limit law that says when you have x to a power, you can just plug in to get the limit. So the answer to this is 2 cubed. I think that was limit law 9. Anyway, so the answer is 8, so it exists. So that's one of the limit laws there, that when you have the limit of x to a power, you can just plug in. So there you go, we get 8. All right, and then I want to write down that the limit of f exists. The limit as x goes to 2 of f of x. Well, on the previous slide, we saw this limit was 2. So it also exists. Okay, so because both limits exist, we can go ahead and use the limit law to get the answer to the one that we're working on. So by the fact that the limit of x cubed exists and the limit of f exists, we have limit as, here's the question again, the original question, x cubed f of x. And again, the limit law says we can put the limit next to each thing. So it's limit as x goes to 2 of x cubed times the limit as x goes to 2 of f of x. Okay, so again, we're applying the limit law there. And then we know that each individual limit, so I'll just write them in there. So limit of x cubed is 8, limit of f of x is 2. So that's it. So the answer to this limit is 16. All right, let's try one more. Okay, so this problem's a little bit more complicated than the last three because it's going to take an extra step. And the reason it's going to take an extra step is because there's an addition here and there's also a root here. In the last three examples, there was just one thing going on. In other words, just multiplication. We could use the multiplying limit law, or just addition, where we use the addition limit law. This time we're going to have to use the limit law that involves roots and the limit law that involves addition. All right, so let's see exactly how we're going to have to write this. Well, basically, here's what we want to do. I'm going to just outline this first. This is not the work you'll show exactly, but let's just outline it so we can see what the work will look like. So what we want to eventually do is to put the limit inside the root. So here's the original question. And you'd want to put the limit inside the root. So we have the root and the limit goes inside. But you're only allowed to make that move if the limit of the inside exists. And because it's an even root, the limit of the inside has to also be positive. So I need this limit to exist and be positive. So I'd have to show you that first. So I'd have to first show you that the limit as x goes to 1 of 3 plus f of x exists and is positive. And to do that, we would probably use a limit law, right? The limit law for sum, which means that the limit as x goes to 1. You can write this limit as x goes to 1 of 3 plus the limit as x goes to 1 of f. So I want to prove to you that this limit exists and is positive, but to do that, you would use a limit law, and you can only use this limit law. You can only go from here to here if this limit exists and this limit exists. So we're going to have to go backwards. So first thing I'm going to do is I'm going to show you that this limit exists and this limit exists. Then I can apply the limit law that goes from here to here. And then when we're done, we're going to hope that this exists. We hope that it exists and is greater than 0. Then I can make this move. So you see what we're going to start with? We're going to start with the limit of 3 and the limit of f. Then we're going to find the limit of 3 plus f. And then we can do the whole problem. Okay, now as far as the limit of 3, we know the limit of 3 exists. That's limit law, what was it, 7, I think, when you take the limit of a number, it's itself. So that one definitely exists. But what about f? We're going to have to look at the picture for f. So let's go ahead and look at the picture real quick. Okay, so to see if the limit as x goes to 1 of f exists, we're going to look at the graph of f. And we're trying to figure out what is the limit as x goes to 1 of f. So we're only going to be using the left graph for this because that's the graph of f. Here's 1. And so to figure out this limit, I'm going to start by looking at the left and the right-hand limits. To find the limit as x goes to 1 from the left, you're going to start somewhere on the graph, but on the left of 1, so somewhere here, let's say. And we're going to move along the graph to the right and get closer and closer to x equal 1. So we're going to be moving this way. And when we get closer and closer to 1, we basically are heading there. And it looks like the outputs are heading towards 1 when you do the left-hand limit. Okay, to find the right-hand limit, I'm going to start on the right of 1, but on the graph. So somewhere here, let's say. And I'm going to move again along the graph and head towards x equal 1. That means I'm going to be moving to the left. And as we head to the left, we're headed towards this spot again. And again, it looks like the outputs are headed towards 1. So it looks like the left and right-hand limits are both 1. So the limit of x goes to 1 of f of x exists and is 1. Okay, so now that we know that exists, we should be able to do the problem. So let's write down, remember we're trying to find the limit of just the inside first. So we need the limit of 3 and the limit of f to both exist. So I'm going to write those things down first. So first thing, limit as x goes to 1 of just 3. That limit exists from limit law 7. Limit law 7 says the limit of a number is itself. So this limit is 3, so it exists. Then we need to say that the limit of f exists. Limit as x goes to 1 of f of x. From the picture, we saw the limit is 1, so it exists. So since each individual limit exists, we can find the limit of the inside, the sum. So by 1 and 2, we have what I'm going to call 3 here. I'm calling it 3 because this is not the end of the problem. So from here we have limit x goes to 1 of 3 plus f of x. We can now use the sum limit law since each individual limit exists. We can write limit x goes to 1 of 3 plus limit x goes to 1 of f of x. Okay, so that's the sum limit law as I go from here to here. And again, you can only make that move if the limit of 3 exists, if the limit of f exists, but we showed each of those things up here. Limit of 3 exists, limit of f exists. So we can make this move, and then we can get the answer, because the limit of 3 is 3, and the limit of f is 1, so this limit is 4. Now that's not the answer to the question, so I'm circling it instead of boxing it. But now we know that the limit of the inside exists and is positive. Remember, when we're going to eventually want to put the limit inside the root. Actually, that's our next step. We can only put the limit inside of an even root if the limit of the inside exists and is positive. So once we found the answer is 4. We can see it exists and is positive. So I'm going to write, so it exists and it's greater than 0. In fact, it's 4. Okay, so since we know that, now we can go ahead and finally find the limit of the whole thing. I am going to have to erase some of this. So let's just remember that we proved that the limit of the inside exists and it's positive. It's 4. And now let me erase everything. And this was called 3. So when I write in a minute, I'm going to say, so by 3, we could put the limit inside the root. Actually, I can just erase this top part. That's probably going to give me enough room here. And so now we're going to write, so by 3, since the limit of the inside exists and is positive, here's what we have. Limit x goes to 1 of the square root of 3 plus f of x. Let me say it one more time. We want to put the limit inside the root. We can only put the limit inside the root if the limit of the inside exists. Because it's an even root, the limit of the inside must also be positive for us to put it inside the root. But in this case, the limit is 4, so it exists and it's positive. So I'm able to put it inside the root. So the limit's going to go inside. So we have a root outside here. We have limit as x goes to 1 of 3 plus f of x. Okay, so we're using that limit law where we can put the limit inside the root, and now we can finally get the answer because the inside we already found. The limit of the inside is 4, and so the answer to this problem is 2. I'll put that in the box because that's the final answer. All right, so that is sort of the end of the easy ones from example 4. Because every limit's existing, everything's working right, we're able to use the limit laws. And now we're going to see a couple of different, more complicated ones where we're going to have to use some kind of trick to figure out the limit. So you'll see what's going to happen when we look at this next problem. Okay, so why is this problem much more difficult than the other ones that we've been working on? I mean, it's just the limit of a sum. So you might think that you just find the limit of each one separately using the limit laws, and that's it, and we're done. Yeah, that sounds correct, except remember, you can only use the limit law on this if the limit of f exists and the limit of g exists when x goes to 1. So in order to use the limit law, the sum limit law, we need limit as x goes to 1 of f to exist. We need the limit as x goes to 1 of g to exist. We need both of them to exist. But in this problem, it turns out that the limit of g doesn't exist. So let's go ahead and look at the graph real quick so you can see what's happening here. So if you look at the graph of f, let's see if we can figure out if the limit as x goes to 1 of f exists or not. So does it exist? Yeah, that limit exists. The reason is because, again, if you start on the left of 1, let's say we start somewhere here, and we head towards x equal 1, moving along the graph. We're headed towards that spot there. It looks like the outputs are headed to 1. If you start on the right side of 1 on the graph, and again head towards x equal 1, both ends, it looks like the outputs are headed to 1. So this limit is 1, no problem. Limit as x goes to 1 of f exists. The problem is, when you look at g, limit as x goes to 1 of g, what's that limit? Well, if you start on the left of 1, so here's 1. So you got to start on the left of 1, but on the graph, let's say here, and you move towards x equal 1, you head towards that open circle up there, and it looks like the left-hand limit is 2. If you start on the right of 1, so let's say we start over here, but on the graph, and you head towards x equal 1, that means we're going to be moving to the left, we head to this filled-in circle, and it looks like the right-hand limit is 1. Okay, So, okay, the right-hand limit's 1. So it looks like the left-hand limit is 2 and the right-hand limit is 1. So it means the full limit doesn't exist. Okay, so we're not going to be able to use the limit law for sums because the limit of g doesn't exist. Okay, so limit of f exists, limit of g exists. Limit of f exists, limit of g does not exist. What's the story with the limit of f plus g? Okay, so let me go over the general idea here. Whenever you have a bunch of functions, added, subtracted, multiplied, whatever it is, and all the limits exist except for one, then most likely the limit of the entire thing doesn't exist. Here we have this limit exists, limit of f, but the limit of g doesn't exist. We have one thing whose limit's not existing, so probably the limit of the entire thing doesn't exist. Now, that's not a rule. I'm not giving you a rule for that, but something to keep in your mind. Okay, so when you get some complicated problem, you go, well, I suspect that it doesn't exist. Of course, we have to know for sure if it doesn't exist or not. So how am I going to prove for sure it doesn't exist? Okay, so let me outline the process here. So first I'm going to outline it, and I'm not going to show it I'm not going to write it exactly the way you should be writing it, but I'll outline it first, and then we'll write it the correct way. Okay, so the idea is, I think the limit doesn't exist, but limit laws are useful when limits do exist. Like, right, for example, when you're using the sum limit law, if the limit of f exists and limit of g exists, then the limit of the sum exists. So limit laws are basically useful if limits are all existing. If a bunch of limits exist, then these other ones also exist. So it's going to be hard unless I can assume that this limit here exists. So basically the idea is I suspect that this limit here doesn't exist. I think the limit as x goes to 1 of f of x plus g of x doesn't exist. I'm going to assume that it does. And then I'm going to do some calculations. And I'm going to show you, hey, if I assume that it does, I end up with something that we know for sure is wrong. And if we end up with something that we know for sure is wrong, then the original assumption must be wrong. And if my original assumption was that this limit exists, then the limit must not exist. That's called a proof by contradiction. So I'm going to assume this limit exists, even though I think it doesn't, come up with something that makes no sense, something that we know for sure is wrong. Our conclusion will be that our assumption, which was that this limit exists, is wrong. Therefore, this limit doesn't exist. And the way we're going to do that is we're going to look at it like this. Again, this is not the whole way to write it yet, just some outline here. So I'm going to assume that this limit exists. Think of this as one function. I know it's two functions being added, but think of it as one entire function. I know that limit exists. I also know the limit as x goes to 1 of just f of x by itself exists. So since the limits of each of those brackets as x goes to 1 exists, if I subtract them, the limit of that exists. So check this out. The limit of as x goes to 1 of f plus g exists because we're assuming it. The limit as x goes to 1 of just f of x exists because we know it's 1 from the graph. So therefore, there's a limit law that says if you take the limit of this minus this, you can put the limit next to each one. And since each limit individually exists, this limit of this whole mess that I have here must exist. But look, I'm subtracting, right? So if you simplify this, this f here and this f here will cancel. So basically they're gone. And you just get that the limit of g exists, which we know is not true from the graph. Okay, let me say that one more time, because I know it's kind of complicated the first time you hear it. And you should also rewind the video a few times if it's still complicated. But let's go over one more time. So I guess I should erase some stuff then. Oops. Okay, so let me say this one other slightly different way maybe. So we know the limit of g doesn't exist. I don't know what the limit of f plus g is, but I think it doesn't exist. So I want to use limit laws though, so I need things to exist. So what I want to end up with is that the limit of g exists. Limit laws will help me end up with something existing. So if I can end up with the limit of g existing, I know something's wrong there. So we're going to make the assumption that the limit of f plus g exists. We're going to conclude that the limit of just g exists. That doesn't make sense because we know the limit of g doesn't exist. Therefore, the limit of the whole thing must not exist. And so what we want to do is we're going to assume that f plus g, the limit of it, exists. So we're assuming the limit as x goes to 1 of this exists. But I want to end up with g. So how am I going to end up with g? I'll subtract off the f of x. And we have a limit law for subtraction, so that's good. And if I assume this limit exists and this limit exists, then we use the limit law for subtraction to say the limit of this whole thing exists. But the limit of the whole thing is just g, since the f's cancel. So therefore the limit of g exists. That's nonsense. Therefore my original assumption that the limit of f plus g exists must be wrong, and so the limit of f plus g does not exist. Okay, so let me go ahead and write it now the correct way. So the writing that I'm about to do is not the most important thing, it's the idea is the most important thing. So if you understood that idea, that you can somehow take f plus g, which we're assuming exists, and combine it with f, whose limit we know exists, and come up with the fact that limit of g must exist, and it doesn't. If you get that idea, then that's really what we want here. Okay, so here we go. First thing I'm going to write down, assume that the limit as x goes to 1 of f of x plus g of x exists. I don't know the number though, so let me call it L for limit. So it exists. Okay, so let's assume that limit exists. Well, we also know that the limit as x goes to 1 of just f exists because we know the limit is 1, so it exists. That was from the graph. So I'm going to subtract these functions. So by 1 and 2, we have limit as x goes to 1 of f of x plus g of x. Think of that as one function. Let me put brackets around it. Minus f of x. This limit exists because we can use the limit law now. We have this limit existing. Think of that as just one function. And this limit existing. So I can put the limit in front of each of those functions from the subtraction limit law. And we get limit as x goes to 1 of f of x plus g of x minus limit as x goes to 1 of f of x. So we can do that since we know each of those limits exists. We know the limit of f plus g exists, we know the limit of f exists, we can do that. And then what's the answer? Well, the first limit is L, second limit is 1, so the limit of this mess here is L minus 1, so it exists. Now basically the idea is that if you simplify this, you just get g, because the f's cancel. I ran out of room, so I'm going to have to erase some stuff here. Let me go ahead and erase. I guess we should leave the assumption up there. Let me erase this part here. So anyway, so simplify f of x plus g of x minus f of x, and you get, so the limit as x goes to 1 of g of x exists. So that's what we end up with. And this is a contradiction because we know it doesn't exist. Contradiction because limit as x goes to 1 of g of x does not exist from the graph. Okay, so just recap all that one more time. I think that the entire limit as x goes to 1 of f plus g does not exist. We're going to prove it by contradiction. So we're going to start off by assuming that it does exist. And then I said, well, if it exists, if the limit as x goes to 1 of f plus g exists, and we already know that the limit as x goes to 1 of f exists, then when you subtract those functions, the subtraction limit law will tell me that the limit of f plus g minus f must exist. But that's just the limit of g. So we conclude that the limit of g exists, but we know the limit of g doesn't exist from the graph. Therefore, the original assumption I made, that's in red here, that the limit as x goes to 1 of f plus g exists, must be wrong. Therefore, limit as x goes to 1 of f of x plus g of x cannot exist, and you're right, it does not exist here. All right, so we're going to try another example somewhat similar to that one. So let's take a look at this one here. All right, so this time we're dividing two functions. We have f of x divided by g of x, and you're going to want to use the limit law, right? You're going to want to say limit as x goes to 1 of the top divided by limit as x goes to -1 of the bottom. That's great. You can do that as long as, well, we need three things to happen. We need the limit as x goes to -1 of the top to exist. We need the limit as x goes to -1 of the bottom to exist. And we need the limit as x goes to -1 of the bottom to not be 0 to use the limit law. So in this problem, what's going to end up happening, we'll look at the graph in a minute, is that both limits will exist, but the limit of the bottom will be 0. Now, if the limit of the bottom is 0, you get division by 0, what are you going to do? Well, we're not quite there in class yet. We'll be there soon. But I just want to give you a little sneak peek here. If the limit of the bottom of a fraction is 0, the limit of the top has to also be 0 for the function to even have a chance of having a limit. Now, again, that's not something I exactly want you to memorize, because I'll show you the right way to do it in a minute. Plus, we want to apply the limit laws, so we want to write it using limit laws. But just something to keep in your mind. For example, if the limit of the top of a fraction is like 7 and the limit of the bottom is 0, probably the entire limit doesn't exist. But if the limit of the top is 0 and the limit of the bottom is 0, don't think that the limit doesn't exist. It could totally exist, and it exists often when that happens. Okay, so one more time. If you're taking the limit of a fraction, if the limit of the top is not 0 and the limit of the bottom is 0, and they both exist, of course, then probably the limit doesn't exist. So let's go and take the graph, look at the graph and see what's going on there at -1. So let's think about limit as x goes to -1 of f, so the left graph here. And to figure out that limit, okay, let's see where -1 is first. So -1 on the x-axis is here, -1. And so if we think about left-hand limits, I'm going to start on the left, move towards x equal -1, and we're headed there. Looks like we're headed towards, this is y equal -1 here. Okay, so it looks like the left-hand limit's -1. If you start on the right of -1, somewhere here on the graph, let's say, and you head towards -1, looks like again we're headed to the same spot. Looks like the outputs are again headed to -1. So the left and right-hand limits are -1, makes the full limit -1, so the full limit exists. So the limit of the top of that expression that we saw on the last slide is -1. Okay, let's go ahead and look at the limit as x goes to -1 of the other function. So the limit as x goes to -1 of g. Okay, so here's -1 on the x-axis. If you start on the left of the graph and you head towards -1, looks like we're headed towards y equals 0. If you start on the right of -1, somewhere here, and again you head towards x equal -1, so that means we're going to move to the left, we're again headed to the same spot, towards 0. So this limit does exist, and it's 0. So the limit of f exists, the limit of g exists, everything's great, except the limit of the bottom is 0. So we're feeling like the limit of f over g probably doesn't exist. Okay, so what we know is the limit of the top is not 0. In fact, it was -1. The limit of the bottom is 0. So the limit of top and bottom both exist. Top is limit is -1, bottom limit is 0. But we also need the limit of the bottom to not be 0 to use the limit law. So we can't use the limit law as it stands right here. Can't just put the limit on top and bottom. Also, in the back of your mind, remember that when you're taking the limit of a fraction, if the limit of the bottom is 0 and the limit of the top is not 0, then probably the limit doesn't exist. So we're guessing it doesn't exist. But again, if we're using limit laws, we want it to exist. We need things to exist to use limit laws. So again, we're going to have to do this by contradiction. We think the limit doesn't exist, but to use limit laws, we want it to exist. So we're going to say, assume it exists. We want to come up with something that makes no sense. And the way it's going to work here is we're going to assume the limit of the entire f over g exists. And then, since we know the limit of the bottom is 0, I'm going to be able to prove to you that the limit of the top must be 0. Remember I said that earlier. If you have a limit of a fraction where the bottom is 0, if the limit of the top is 0, it could exist. But if the limit of the top is not 0, it will never exist. That's, again, not a hard set rule, but something to keep in the back of your mind. So I'm going to prove to you that the limit of f must be 0. And if I prove to you the limit of f must be 0, we know that's wrong. We know the limit of f was -1. So that's going to be our contradiction. That's going to be the wrong thing that we end up with. And so we can conclude that this limit of the whole thing actually doesn't exist. How are we going to get f from this stuff? So the idea is I want to have f over g in there. Remember, this is a sketch for now until we actually write it out correctly. But I want to end up having an f of x over g of x somewhere. And I'm going to assume that limit exists. And I want to somehow get just f. So the idea is we're going to multiply it by g. You guys agree if we multiply by g, we just get f, the g's cancel? But if I make the assumption that this limit exists, and we know this limit exists, it's 0, then the limit of the entire thing will exist from the multiplication limit law. But then that would mean that the limit of f exists. Now we know it exists, but there's an extra thing here, that the limit of g is 0. So when we use the limit law, we're going to get some limit here times 0. And remember, these cancel, we just get f, and we'll get that the limit of f is 0. So that's the idea. Okay, let's write it out the correct way. So again, we're going to make an assumption. So let's assume that the limit is x goes to -1, of the entire fraction exists, and we'll call it L. So it exists. Okay, we also know that the limit of g exists. The limit is x goes to -1 of just g of x. We know the answer is 0, so it exists. So by 1 and 2, we can find the limit as x goes to -1 of f of x over g of x. Think of that as one function, that whole mess there. So I'll put brackets around it, times g of x. Again, why am I doing this weird one? Why am I doing f of x over g of x times g of x? Because it's going to give me f of x, and it's going to tell me something about f. So the limit law for multiplication says you do limit as x goes to -1 of the first one, which is this whole mess. Again, think of it as one thing, times the limit as x goes to -1 of g of x. Okay, so again, we're allowed to make that move because the limit of f over g exists because we're assuming it, and the limit of g exists because we already know the answer is 0. So then this answer must be, well, the first limit, we called it L. The second limit is 0, so the limit of the entire thing must be 0. Okay, so that's great. But again, remember that this thing here, this expression here, when you simplify it, you just get f. I'll go ahead and write that in a second. But the conclusion is that the limit of f is 0. So, okay, let me erase some stuff so I can write that here. Let's erase this line. Okay, and we'll erase this a little bit here. Okay, so what did we get? We got that the limit as x goes to -1 of f of x equals 0. Remember, again, after you simplify this, the g's cancel, and you just get f. So our conclusion is that the limit as x goes to -1 of f is 0. Now that's definitely wrong. That's a contradiction. Contradiction. Why? Because earlier I showed you that the limit of f was -1. It's not 0. So it's a contradiction. Okay, so we assumed that the limit of f over g existed. Remember, we thought the limit didn't exist, so we assumed that it existed. We concluded that the limit of f must be 0. And that's definitely a contradiction because it's not. Therefore, our assumption must be wrong. our assumption that the limit of this limit existed must be wrong. So we now know that the limit as x goes to -1 of f of x over g of x does not exist. So a quick recap on this here. What happened was, or maybe I'll say it this way. Whenever you take the limit of a fraction, if it exists, and the limit of the bottom is 0, then the limit of the top must also be 0. That's basically what we proved. So in this problem, the limit of f existed, the limit of g existed, but the limit of g was 0. And you might automatically go, oh, then the limit doesn't exist. No, the limit could still exist if the limit of f is 0. In this problem, the limit of this was not 0, so non-zero. And this one was 0. When the limit of the bottom is 0 and the limit of the top is not 0, that's when the limit of the whole thing doesn't exist. So we're pretty sure that the limit of the whole thing doesn't exist. We assumed that it did. We were able to conclude, since the limit of g is 0, that the limit of f must also be 0. So we concluded the limit of f is 0. But that's not the case, because we know the limit as x goes to -1 of f equals -1 from the graph. So therefore, the thing we wanted, limit, doesn't exist. All right, let's go ahead and look at another example. Okay, this one's a fun one. Remember, we don't have much to go on right now. What do we know? We know how to find limits from tables, but those aren't so great. We know how to find limits from graphs. We have limit laws, and we know that if the left and right hand limits are the same, then that's what the full limit is. A couple extra little things that we learned in this video so far. If you have a bunch of functions all combined together, and every limit exists except for one, probably the whole limit doesn't exist. And if you have the limit of a fraction, if the limit of the bottom is 0, then the only way the limit of the whole thing can exist is if the limit of the top is 0. Those are some things just to keep in mind. Now we're going to have to be a little clever on this one here. So in this problem, we have two functions. We have f and g. We have their graphs there. And it says to find the limit as x goes to 2 of f times g. So that's the question there. Well, your first thought should be, okay, it's multiplication. We're going to use the multiplication limit law. Do the limit of f, limit as x goes to 2 of f, times the limit as x goes to 2 of g. So this is wrong, but for example, this should be your first thought, okay, that you go limit of f times limit as x goes to 2 of g. And I can't stress it enough, you cannot make this step. I'm not even allowed really to write this down unless the limit of f exists and the limit of g exists. Does the limit as x goes to 2 of f exist? It doesn't. If you look at f and you start on the left of 2 and you go towards 2, it looks like the left-hand limit is 1. But if you start on the right of 2 and you head towards 2, it looks like the limit is 2. So the left-hand limit of f exists, the right-hand limit of f exists, but the full limit doesn't exist. So this limit doesn't exist. So we weren't allowed to do this move here. Okay, so that was a bad move. Let's go ahead and look at g. The limit as x goes to 2 of g. If you start on the left of 2, let's say we start here, and we move towards 2, we head towards this filled-in circle here, which is at 4. That tells me the limit as x goes to 2 from the left of g is 4. We start on the right of 2, so we start somewhere here, let's say, and we follow the graph towards 2. Okay, that was really sloppy. I need to erase that and draw it again. So we're starting on the right of 2, and we follow the graph towards 2. We end up heading towards this open circle here, and that's at 2. Looks like the limit as x goes to 2 from the right of g of x is 2. So the limit of g of x doesn't exist either. Now I said in the previous problem, or actually 2 problems ago, that if the limit of everything in your function except for one of them doesn't exist, then probably the whole thing doesn't exist. But this time I have 2 of them not existing. Does that mean therefore it doesn't exist? Your first instinct might be yes, but I don't know. It could totally exist. In this problem, it actually does exist, and it's, in a sense, if this makes any sense, the does not exists are kind of canceling each other out, something like that. Okay, so I want to use the limit laws to figure out this limit. And again, to use the limit laws, I need limits to exist. These limits do not exist. These are full limits. But here's the idea here. We know that left and right hand limits exist. For f, okay, so for this one here, we know the left hand limit exists, it's 1. The limit as x goes to 2 from the left of f exists, it's 1. The limit as x goes to 2 from the right of f exists, it's 2. For g, the left and right hand limits as x goes to 2, again, they both exist. So how we can use limit laws when full limits don't exist? Well, we can just go ahead and do left and right hand limits. So the idea is, instead of finding the full limit as x goes to 2 of f times g, let's go find the left and right hand limits of f times g. And when we're doing left and right hand limits, all the limits in sight exist. So limit laws can be used even if you're just doing left or right hand limits. That's, I guess, the idea. Okay, so let's focus on left-hand limits right now. Just left-hand limits for each of these things here. So I already showed you in the last picture, but let me write it down. So limit as x goes to 2 from the left of f of x is 1. And it exists. Again, I'm only doing left-hand limits right now. Let's go ahead and look at g though. Limit as x goes to 2 from the left of g, that also exists, and is 4. Okay, so remember the idea? We're going to try to find this limit by using left and right hand limits. So here's what we're trying to find. Limit as x goes to 2 of f times g. First, we're going to find limit as x goes to 2 from the left of f times g. Okay, so to use the limit law on that, I need to know that the limit of each one exists. So I'm going to write that down. We do know that it exists. The limit as x goes to 2 from the left of f of x is 1. So it exists. It's from the graph, or the last slide if you want. Then we also know that the limit as x goes to 2 of g from the left. Again, everything is left-hand limits for this example here, or for this part of it. The limit as x goes to 2 from the left was 4, so it exists. Okay, so since both left-hand limits exist, I can find the left-hand limit of f times g. So by 1 and 2, the limit as x goes to 2 from the left of f times g, we're allowed to use the limit law since each one exists. So the limit as x goes to 2 from the left of f times the limit as x goes to 2 from the left of g. And we know those limits, so it's 1 times 4, so it's 4. So that is the limit as x goes to 2 from the left of f times g. All right, so now the idea is we're going to find the limit as x goes to 2 from the right of f times g. If it's also 4, then we'll know the full limit is 4. All right, so let's look at that now. Here's the graph again. Let me go ahead and look at just right-hand limits. So we know they exist, but let me write them down. Limit as x goes to 2 from the right of f. You can see it's 2, so it exists. Limit as x goes to 2 from the right of g. Remember, this is only right-hand limits we're working on right now. This one is also 2, so they both exist. Okay, so now we're going to find the limit as x goes to 2 from the right of f times g. And same idea, we're going to use the limit law, which we can use now because the right-hand limit of each one individually does exist. So limit as x goes to 2 from the right of f is 2, so it exists. The limit as x goes to 2 from the right of g is also 2, so it exists. So by 1 and 2, we can find the limit as x goes to 2 from the right of f times g. The limit as x goes to 2 from the right of f times g. Again, we're allowed to use the limit law because each individual limit exists. So this limit exists, so it's the limit of f times the limit of g. And we get 2 times 2, so we get 4. And that is the right-hand limit. Okay, and then the thing is that, so the left-hand limit exists and the right-hand limit exists, and they worked out in such a way that they were equal. In the left-hand limit case, it was 1 times 4, so the left-hand limit was 4 of f times g. And for this one, for the right-hand limit, it became 2 times 2. Again, it turned out to be 4. So again, it was kind of sneaky, but kind of interesting that the left and right-hand limits both exist, even though the full limits of each one don't exist. But so the full limit of f doesn't exist, the full limit of g doesn't exist. But I don't care about those limits. I care about the limit of f times g. And the left-hand limit of f times g does exist, it's 4. The right-hand limit of f times g does exist, it's 4. So we can figure out what the full limit is. Since they're equal, it's going to be 4. Go ahead and write that down here. So just write that down. So since the left-hand limit, so limit x goes to 2 from the left of f times g, we already found, is equal to 4. And the limit as x goes to 2 from the right of f times g is also 4. The full limit as x goes to 2 of f times g, full limit, is 4. It's very interesting, if you ask me. Also, another thing that's interesting is that the limit of f doesn't exist. The limit of g doesn't exist, but when you multiply them, at least in this example, they do exist. I'm not saying when you take 2 does not exist and multiply them, they always exist, but this time it turned out to exist because when we looked at left and right hand limits, both times we got 2 numbers multiplied together that gave us 4. All right, let's go and look at another example. Okay, so in this example, we don't have the graphs like we did in the other one, but we just have 3 functions, f, g, and h. We don't know what they are. We just know the limit as x goes to 2 of each of them. They all exist. The limit of f as x goes to 2 of f is 4. The limit as x goes to 2 of g is negative 2. The limit as x goes to 2 of h of x is 0. And it's asking us to find all these other limits here. Okay, so once again, I'm going to do these problems, but I'm not going to do them in the order that they're written here because I'm trying to remember how many of them are much more difficult than the other ones. So some of them are easy. Again, some of them are a little more complicated. So I'm going to do the easy ones first. The easy ones are kind of like more practice. So I think A is definitely one of the easier ones. So we're going to start with A. Okay, so we want to find this limit, and we have a sum here. So your first instinct would be to find the limit using the sum limit law. Again, this is not the work yet. I just want to outline the work first. So you want to write, eventually, limit as x goes to 2 of f of x plus limit as x goes to 2 of 5g of x. But of course, you can only write that if the limit of f exists. Now that's given, so that's not a problem. And if the limit of 5g exists, that's not given. So I'd have to first show you before that the limit of 5g exists. And to show you that the limit of 5g exists, I would want to use the limit law where you copy the number in front down and take the limit of the rest. But of course, you can only use that limit law if the limit of g exists, which of course we know that it does since it's given. So I'm going to have to start off by showing you that the limit of g exists. And that's given. Then once I show you that, then I can show you the limit of 5g exists by using this limit law. And then once I state that the limit of f exists, and we already know the limit of 5g exists, then we find the limit of the whole thing using the sum limit law. Okay, so that's the order we're going to have to go in. Okay, so we want to first deal with the 5g. Okay, so let's write this down. The limit as x goes to 2 of which function? I want to get to 5g, so I have to write g first. So limit as x goes to 2 of g is negative 2, so it exists. Because of 1, so by 1, we have what I'm going to call 2. The limit as x goes to 2. The 5g, remember when there's a number in the front, the limit law says you copy the number down and take the limit of the rest as long as the limit of the rest exists. And it does because I just showed it in the previous step. So it's 5 times negative 2. So it's negative 10. So it exists. Okay, so we have the limit of 5g existing. Okay, and then 3, the limit as x goes to 2 of f is given as 4, so it exists. And since the limit of f exists now and the limit of 5g exists, then we can use the sum limit law and do the whole thing. So now I'm going to write down by 2 and 3. Here's the question now. Limit as x goes to 2 of f of x plus 5g of x is equal to the limit as x goes to 2 of f of x plus limit as x goes to 2 of 5g of x. And so let's see, so limit of f is 4, and limit of 5g is negative 10. Oops. So the answer is negative 6 to that one. Negative 6. Yeah, so that's how that one goes. Pretty straightforward, just a couple of steps. You have to take care of the 5g first before you did the sum limit law. So use the number in front limit law and then the sum limit law for that one. All right, let's go ahead and try part B. Okay, so the idea here is we have a function and then a power, and there's a limit law that says when you have a function to a power, you can put the limit inside the bracket there as long as the limit of the inside exists. So this one's actually pretty straightforward. It's only one step here. So I'm going to write down that the limit of g exists first. Limit as x goes to 2 of g of x. Well, it's given to us. It's negative 2. So it exists. So we can do the problem now. So because of the fact that the limit of g exists, we could do the problem. And I'll write down the question now. Limit as x goes to 2 of g of x cubed. The limit law says you can put the limit inside the bracket. So bracket first. Limit as x goes to 2 of g of x cubed. By the way, let me mention another thing about this limit law where you put the limit inside the bracket. It's going to be important eventually, so I might as well mention it now. You can only put the limit inside the bracket if the power out here is a number. For example, if that power had some letters in it, like an x or sine x or natural log x, you're not allowed to do that. Or maybe there's a way you can get around it and you can do it. But the limit law that I gave you specifically, this power has to be a number and actually has to be a positive whole number. But it is. So we're allowed to do that here. Okay, so that's pretty much it. The limit of the bracket is negative 2, so this is negative 2 cubed, which is negative 8. So that's just an example of using that limit law where you put the limit inside the brackets. All right, now we're going to look at a similar one where you put the limit inside of a root. That's part C. All right, so again, the idea is when you have a limit of a root, you want to put the limit inside the root. But you got to remember when you can. When it comes to roots, it's just a little extra business going on. I need the limit of the inside to exist, so I need the limit of f to exist. But I also need the limit of the inside to be greater than 0 when the root is an even root. Is it an even root here? Yeah, it's a square root, so it's an even root. So I need the limit of the inside to exist and be positive. So you just have to write that down. Other than that, it's a pretty easy problem. So first thing you do is you write down just the limit of the inside. Limit as x goes to 2 of just the inside. It's 4. So it exists. And is greater than 0. So please make sure you put the greater than 0 part. Because if it's not greater than 0, you can't put it inside of an even root. Okay. So by the fact that the limit of the inside exists and is positive, we can do the problem now. Limit as x goes to 2 of square root of f of x Again, you put the limit inside the root, so you put a root first, and the inside is going to be limit as x goes to 2 of f of x. And so we have square root of, what was the limit? 4. And so the answer is 2 to that one. Yeah, that's how that one goes. All right, let's try the next one. Okay, so this one just takes 2 steps. You know, we need the limit of the top and the limit of the bottom to exist before we can use the division limit law. The limit of the bottom also has to not be 0. The limit of the bottom is not 0, it's -2, so that's great. And we also need the limit of the top to be to exist. So we're going to have to actually show that first. So again, the idea is we're going to first show you that the limit of the top exists. Then I'll use the division limit law. So it's a couple of steps here. So the first thing I'm going to write down is, again, I'm working on just the top. So for the limit of the top, we need to know if the limit of f exists. So let's go ahead and write that down. So limit as x goes to 2 of f of x is 4. So it exists. Okay. So then we can work on the top. So by 1, we have what I'm going to call 2. The limit as x goes to 2 of 3f of x. Well, what was the rule when you have a number in the front? You copy down the number in the front and take the limit of the rest. As long as the limit of the rest exists, but we found that the limit of the rest exists right here. So it's 3 times 4, so 12. So now I know the limit of the top exists. So let me write down the limit of the top exists. You can just write so the limit exists, but I just thought I'd write a little more there. Okay, so the limit of the top exists. And incidentally, it's 12. Okay, I need some more room to finish this problem, so let me go ahead and erase some stuff. Okay, so we just showed that the limit of the top exists. Now, I need to mention that the limit of the bottom exists, and that's going to be 3. Okay, so the limit of the bottom it's -2, so it exists. What else do I need? We're going to use the division limit law in a minute, so I need the limit of the bottom to exist and not be 0. Not greater than 0. Greater than 0 is for even roots, but I need it to not be 0. So it exists and is not 0. Okay, so now we can finally do the problem. So because of the fact 2 was that the limit of the top exists and it's 12, and by 3, which says the limit of the bottom exists and is not 0, we can do the problem. So we have limit as x goes to 2 of 3f of x over g of x. Again, you're just going to put the limit. For the division limit law, you just put the limit one time on top, and then one limit on the bottom. And we know both of these limits, so we just basically write them in there. Limit of the entire top was 12. Sorry, that was earlier. I erased it already. And limit of the bottom is -2. And so the answer to this whole limit is -6. Okay, that's how that one goes. Okay, we're going to do one more, call it easy one. So let's take a look at this one. Part F. It's similar to the one we just did. But again, it's going to take a couple of steps. I need to show you the limit of the top exists, so that's going to take a little bit of work. And then I'm going to show you the limit of the bottom exists, and I'm going to show you the limit of the bottom is not 0. Then I'll be able to use the division limit law and we can finish it off. But again, I'm just going to work on the top right now. Okay, so work on that. First thing, the top needs the multiplication limit law. That means I need the limit of g and h to both exist. So I'm going to write those things down. Limit as x goes to 2 of g is -2, so it exists. Okay, then we're going to work on h. Limit as x goes to 2 of h is given to be 0, so it exists. And then we can use the multiplication limit law. So I'll call that, so okay, right. So by 1 and 2, we're going to have 3. The limit as x goes to 2 of g times h. Again, since each one exists, we can use the multiplication limit law and just do the limit of each one separately. Limit as x goes to 2 of g times limit as x goes to 2 of h. The first one is -2, second one is 0. So the answer is 0. Maybe I shouldn't have boxed that because that's not our final answer. But we just found out the limit of the top is 0, and so it exists. Don't let 0 bother you. It's the limit of the top. Limit of the top being 0 is not a problem. Okay, so now I need to show you that the limit of the bottom exists and is not 0, and then we can use the division limit law. So that's going to be part 4 here. Let me erase some stuff. Okay, so now let's work on the bottom. We'll call that 4. So we have limit as x goes to 2 of f is 4. What do I need to happen here? I need it to exist, which definitely exists. And what else? Because I'm about to use the division limit law, I need the limit of the bottom to not be 0. So I'm going to write so it exists and is not 0. Again, greater than 0 would be wrong. I don't need it to be greater than 0. But I need to be not 0 to use the division limit law. Okay, so we have the limit of the top existing, and the limit of the bottom existing, and the limit of the bottom is not 0, so I can use limit law. So this is so by 3. 3 was that the limit of the top exists, and it happened to be 0. And 4, that the limit of the bottom exists and is not 0. Here's the question now. Limit as x goes to 2 of g of x over 8, g of x h of x over f of x equals, so I'm just going to put one limit up on top. And one limit on the bottom. And the limit of the top is 0. The limit of the bottom is 4. And so the entire limit is 0. So that's how that one goes. Okay, let's take a look at the next one. Okay, so this is a similar problem to one we saw in example 4. It looks like we want to use the division limit law, but we can't. In order to use the division limit law, don't forget, we need the limit of the top to exist, and the limit of the bottom to exist, and also the limit of the bottom to not be 0. Well, yes, the limit of the top exists, and yes, the limit of the bottom exists, but the limit of the bottom is 0. So when that happens, what did we say? Well, we said the thing to keep in mind was if the limit of the bottom is 0, so the limit of the bottom is 0, so if this is going to 0, and if this also goes to 0, then the limit could exist. But the limit of the top is -2. So this limit of the top over here is -2, and the limit of the bottom is 0. So one thing I told you to remember is if the limit of the top and bottom both exist, and the limit of the bottom is 0, then the only way this limit could exist is if the limit of the top is 0, but the limit of the top is not. So our feeling is the limit here doesn't exist at all. Okay, but of course, how are you going to prove it? So this is what we're going to do. Again, we're going to do a proof by contradiction. We're going to assume that the entire limit exists. And then I'm going to somehow try to show you that the limit of the top, therefore, must be 0. So if we assume the entire limit exists, and we use the fact that the limit of the bottom is 0, I want to somehow convince you that the limit of the top is 0. And then, of course, you know the limit of the top is not 0, and that'll be the contradiction. So it's very similar to that problem we did in example 4. So let's see how we're going to do this. So one more time real quick, let's remember, I think the limit doesn't exist, but to use limit laws, we want limits to exist. So we're going to do a proof by contradiction. I think the limit doesn't exist, so I'm going to assume it does. And I'm going to do some calculations until we end up with something that's wrong. Then we'll know our assumption that this limit exists is wrong, and therefore the limit must not exist. So when you do a proof by contradiction, first thing I'm going to say is, we'll call this 1, assume that this limit, the limit of the entire thing, exists. I should call it something, so I'll call it L for limit. So I'll assume this limit is L. So it exists. Okay, so let's assume this limit exists. Well, the next thing is we know that the limit of the bottom exists. Limit as x goes to 2 of the bottom exists. So by 1 and 2, we're going to look at this limit. Well, what limit are we going to look at? I'm going to make up something that's equal to g, but I want to use the limits that we know. We know g over h, so I want to get g over h in there. So I'm going to put g over h, and I'm going to write it in brackets. We're thinking of that as one piece. So that limit exists. And then I'm going to multiply it by h, because when you multiply it by h, you just get g. Okay, so since the limit of g over h exists, and the limit of h exists, we can use the product limit law on this when we have g over h times h, and we get that this equals limit as x goes to 2 of g of x over h of x times limit as x goes to 2 of h of x. Okay, first limit is L, second limit is 0, so this whole limit is 0. Okay, so if we make the assumption that this limit that we're trying to find exists, then we conclude that the limit of this mess here is 0. Now, of course, if you notice this mess, if you simplify it, the h's cancel. And so basically we just learned that the limit of g is 0. And of course we know that's not the case because up here it says limit of g is 2. All right, so let me erase some stuff here to write down the conclusion. But you see we're getting a contradiction. We're concluding that the limit of g is 0, but that's a contradiction. So therefore my initial assumption must be wrong. And that's how proof by contradiction works. So what are we going to write down? Okay, so we just found out that the limit as x goes to 2 of g of x equals 0. But it's not from this. So we have a contradiction. And what does this contradict? Well, it's a contradiction, it's something wrong. Therefore, the initial assumption that the original limit exists, this assumption over here, must be wrong. So let me go ahead and erase the bottom and go ahead and write down the final conclusion here. Okay. So the limit that we originally started with must not exist. Okay. So that's how that one goes. All right, we got a couple more. Okay, so there's a couple of different ways that this one can be handled. One thing I want to mention to you is that whenever you are taking a limit as x goes to 0 in this case, what does that mean? It means you're going to be, if you plug in numbers closer and closer to 0, but not 0, what are the outputs getting closer and closer to? Because this is a full limit, we're supposed to be plugging numbers on both ends of 0. So as far as the function goes, this part here, I don't care at all what happens when you plug in 0. I don't care if you get an answer. I don't care if it's undefined. I don't care. But I care what's happening near 0. And it's the full limit. I care what's happening on both sides of 0 as long as you're not plugging in 0. So whenever you have something that says limit as x goes to 0, the number is not important, but let's just, okay, it says 0. I need the function to be defined everywhere close to 0. So this function here has to be defined on both ends of 0. Let me go ahead and draw a number line here real quick. Imagine this is just a number line. X-axis, think of it as inputs, and I'll put 0. Okay. Again, the function doesn't have to be defined at 0. Okay, so I don't care what's happening there. But it must be defined at all numbers sufficiently close to 0 on both ends. There must be some open interval, some interval, So that you can plug in any number in this interval into that function. You should be able to plug in any number, except I don't care if you can plug in 0. So any number here and any number here. But as far as natural log goes, you can't, the inside of a natural log must always be positive. The inside of an ln must be positive. So basically that means you can't plug in any numbers on this side of the x-axis into this because you'd get undefined. So whether the limit, the right-hand limit exists, when you plug in numbers on this side or not, this full limit cannot exist because you can't even plug in numbers on this side. So that's one reason to explain that this limit doesn't exist. Let me go ahead and write it like this. So because the function 2 plus natural log x is not defined at numbers less than 0, the left-hand limit does not exist, which implies that the full limit doesn't exist. So this is a domain kind of argument. So we're looking at the domain and we're saying there are no negative numbers in the domain. So we can't even ask about a left-hand limit. So this doesn't have a left-hand limit. The left-hand limit doesn't exist, so the full limit doesn't exist. Okay, that's one way of proving this. Let me go ahead and show you a second way. So a second way to prove that this limit doesn't exist is by contradiction. Let's go ahead and take a look at the graph of natural log x first. So let's draw an x and y axis. Natural log x has an asymptote, which is the y-axis, and it goes like that, something like that. That's y equals natural log x. So again, you see that it's not defined on this side of 0. And even on this side, if you were looking for like a right-hand limit, the graph doesn't look like it's settling down to any particular y-coordinate. It's going lower and lower. So the limit as x goes to 0 of natural log x, just natural log x, does not exist. We also saw this in class already, but I just wanted to remind you. So limit of natural log x, limit as x goes to 0. It has to say x goes to 0, but limit as x goes to 0 of natural log x doesn't exist. Okay. But now this question is not asking us to find the limit of natural log x, it's asking us to find the limit of 2 plus natural log x. So you would think you would use a limit law to try to figure this out. You use the sum limit law, but you can't. Why can't you use the sum limit law? Because if you did, you would get limit of 2 plus limit of natural log x, but the limit of natural log x doesn't exist. So you can't use the limit law. Okay, so then what can we do? Remember, limit laws work well when every limited site exists. And I mentioned to you in a previous example that if the limit of everything exists in your function except for one term, then the limit of the whole thing probably doesn't exist. In this case, the limit of 2 exists, but the limit of natural log x doesn't exist, so probably the whole entire limit doesn't exist. But we'll prove it by contradiction. We'll assume it does exist. We'll try to come up with nonsense. The way it's going to work in this problem is we're going to assume that the limit of the entire function exists, and I'll try to convince you that the limit as x goes to 0 of natural log exists. And then, of course, we know that's not the case. That'll be a contradiction, so this whole limit won't exist. Okay, let's do some more erasing. Okay, so first we're going to write down assume. Remember, I think the limit doesn't exist, so I'm going to assume it exists. Assume limit as x goes to 0 of 2 plus natural log x exists, and we call it something equals L, and so it exists. Okay, well, I'm going to basically subtract 2 and then say, okay, then the limit of, if you subtract 2, you just get natural log x. So I guess I have to write something about 2. So the limit as x goes to 0 of 2, we know that exists. That's limit law 7. It's equal to 2, so it exists. So by 1 and 2, if I subtract these functions, that limit will exist. So limit as x goes to 0 of 2 plus natural log x minus 2. Okay, so I'm subtracting them. The limit law says, since the limit of this exists and the limit of this exists, I can put the limit next to each one when you're subtracting. So it becomes limit as x goes to 0 of 2 plus natural log x minus limit as x goes to 0 of 2. The first limit is L, the second limit is 2. So this limit is L minus 2. So that's a number, so it exists. But again, what is that showing us? If you look at the limit that I just found, these 2's cancel. And basically I'm saying the limit of natural log x cancels. So I'm going to go and write that down now. So the conclusion is, so the limit as x goes to 0 of natural log x exists. But we know that can't be the case. We already know this limit doesn't exist, so that's a contradiction. It contradicts this initial assumption that the limit of 2 plus natural log x exists. If we make that assumption, we can conclude that the limit of natural log x exists, but it doesn't. So the original limit must not exist. So let's go write that down. So the original limit does not exist. Okay, so that's how you can do that one, and just another example of how you can use contradiction and the limit laws to prove a limit doesn't exist. All right, guys, just a couple more. Let's go to the next one. Okay, so this is again similar to the last one. It says limit as x goes to 0. So it's a full limit. So in order for this limit to make sense, the function that we're finding the limit of, so this guy over here, has to be defined. I don't care if it's defined at 0, in this case it's not, but it has to be defined at all numbers close to 0 on either side of 0. So you should be able to plug in positive or negative numbers. And again, this is undefined when x is less than 0. So that means the left-hand limit doesn't exist. In other words, there's no graph even there. Left-hand limit doesn't exist, so the full limit can't exist. The full limit can't exist because, for example, if the full limit was 3, then the left and right hand would both be 3. But the left hand does not exist, so the full limit must not exist. That's one way to do it. And probably the only way to do it, because I'm trying to think of a contradiction way for this one to work, but I don't see exactly how it would work. I would think, for example, if you assume that the whole limit exists, then you try to divide by x or something and try to get that the limit of natural log exists, which it doesn't. But if you divide by x, x is going to 0, we're going to have division by 0 in the denominator. So I don't really see a contradiction working for this one. So I think the only way to do this one is to say, hey, you can't do limit as x goes to 0 because the left-hand limit doesn't exist just because there's no function there. So that's good enough argument for that one. All right, one more. All right, so I think I saw this in the homework somewhere and I thought it was pretty interesting. You can totally use the limit laws here, but you can't use them in the way you would think. Like if you don't think about it too hard, then you're not going to be able to use it. Like for example, you don't just take the limit of the top and the bottom, even though the limit of the top and the bottom both do exist, but the limit of the bottom is 0, so you can't use the division limit law. But we're going to be able to get around that if you think about it for a little while. And let me just go ahead and tell you the secret if you want to think about it for a minute first and go ahead and pause the video. And so let me go ahead and tell you what it is. So what we're going to do is we're going to use a trig identity. There's a trig identity for sine 2x. Now, why would I think to even use a trig identity? Because the trig identity for sine 2x, let me go ahead and write it down. Sine 2x is 2 sine x cosine x. And why is that better? Because if I have a sine x up on top here, we're going to have a sine x over x, and we know something about the limit as x goes to 0 of sine x over x. So that'll help us. So what would end up happening, I'm going to do the work over in a minute, but let me go ahead and just show you what's going to end up happening first. We're going to have limit as x goes to 0 of 2 sine x cosine x over x. And again, the x on the bottom is the problem because I can't use the limit law. But now I can just rewrite the function. So we can write it like, so we have the 2, which is not a problem. Then I can write sine x over x, which we know about already, and then cosine x. And all these things are getting multiplied. Okay, and then we can use the, oh, I forgot the 0 here. Then we can use the multiplication limit law and do like the limit of each thing separately, where I'm thinking of, when I say each thing separately, I mean limit of this, and limit of this. And as far as the first thing, one thing is concerned, you could just think of it as a number in the front instead of the multiplication limit law. Okay, so if you think of them, you kind of have to take the sine x over x and think of it as a group, and then I know the limit as x goes to 0 of it is 1. And then the other ones you just take individually like that. Now we haven't talked in class about the limit as x goes to 0 of cosine x, so for now let's just say you can look at the graph, or you can just go ahead and plug in 0 and get the answer. But again, I didn't mention that in class yet. So for right now, let's just say you look at the graph of this, and let me just say, pretend that you did look at the graph and that limit would be 1. So basically use the limit law, the multiplication limit law, and get that that's 1. Okay, let me go ahead and erase stuff now and write it out a little bit neater. Okay, so to be technically correct on everything, I'm going to go ahead and do it like this. First, let's think about limit as x goes to 0 of cosine x, and I'll just say that we drew a graph. Let me go ahead and draw the graph here. Again, I'll have other things to say about this another day, but for now, the graph will tell us the limit of this. So the graph of cosine looks like this. And here's x equals 0. And you can see if you start on either side of 0 and follow the graph towards x equals 0, on both ends we head towards the peak there, which is at 1. So this limit is 1. So this limit exists. So that would be my first thing I'm going to write down, that this limit is 1, so it exists. And of course, it's by the graph. Second thing I'm going to write down is that the limit as x goes to 0 of sine x over x is 1, so it exists. How do we know? Well, we saw that in class we saw that this limit equals 1 from a table. Of course, that's not the best way to do it. I also told you to memorize it. So for now, let's just believe it. One of these days I may make a video to prove that that limit's actually 1, but for now we'll believe that. And so by 1 and 2, if you wanted to take the limit as x goes to 0 of sine x over x times cosine x, we're going to use the multiplication limit law here. It's going to be limit as x goes to 0 of sine x over x times limit as x goes to 0 of cosine. So you get 1 times 1, so you get 1. Oops. Let's make that a little bit neater here. Okay. 1 times 1, so we get 1. Okay. And so we can finally finish off the problem. Let me go ahead and call this 3 actually. Okay, so the limit of sine x over x times cosine is 1. Let me erase some stuff. So finally we can find the limit that they're asking us to find. So we have limit as x goes to 0 of sine 2x over x. All I'm doing here is just rewriting the function using trig identity. So we have 2 sine x cosine x for the top over x. Okay, and then we can rewrite the function a little more. I'm not even using any limit properties yet. All I'm doing is rewriting the function in a way to where it's easy to use the limit law. So I'll write 2 times sine x over x times cosine x. And I'm going to put this in a bracket because we just found that limit to be 1 a few seconds ago. And so now, here I'm going to write down by 3. By the fact that we know that this limit exists. How do you find the limit when there's a number in the front? The answer is you copy the number down and you take the limit of the rest. Remember, you can only use this, you can only do this step if the limit of the rest exists, but we showed by 3 that it does and it's equal to 1. And so finally we have 2 times 1, so the limit here is 2. All right, that was a super long video, but I hope it made some sense. Hope you enjoyed it. Study hard, and I'll see you next class.